solutions to nth order homogeneous linear ordinary differential equations. For cases 3 and 4, we'll be taking up complex and distinct roots and complex and repeated roots. So for case number 3, for the complex and distinct roots, we have basically imaginary roots, and then they are conjugate complex roots. So let's just say the roots are m is equal to 0 plus and minus I. I can say that A here is 0 and then B is 1. And then the plus and minus because they are conjugate pairs. If you recall last time when we had the real roots, E to the mx is one of the solutions. So in this case, if m is 0 plus and minus I, that means your m number 1 is 0 plus I. Your m number 2 is 0 minus I. So let's just take, for example, the 0 plus I. This would be E 0 plus I times x, right? And if it's 0 minus I, it's going to be E raised to 0 minus I x. So we use what you call Euler's formula. For the Euler's formula, E raised to A plus B I, it gives us E raised to A quantity cosine B plus I sine B. So it takes care of the A and the B. But then if, for example, if we have an X, of course, this would have an X and then this would have an X as well. So if the characteristic equation, f of m, has imaginary roots m1, a plus bi, and m2, a minus bi, your solution would then be y is equal to c1 e to the a plus bi x plus c2 e to the a minus bi x. And then using the Euler's formula, you'll have, take note that e raised to a plus bi would give us e to the a cosine b plus I sine b. So using this, you can express the above equation into this one. C1 e to the ax, quantity cosine of bx plus I sine bx, plus C2 e to the ax, cosine of negative bx, plus I sine of negative bx. And then do take note that cosine of negative bx is still cosine of bx, whereas sine of negative bx is basically negative sine bx. All right? So when we combine this, like we combine both cosines in this case, you can say that that's basically C1 plus C2. And then this one, when you combine both sines, C1, and then take note that sine of negative bx, according to this one, is negative of sine bx. That's why this becomes C1 minus C2. So in here, if I say C1 plus C2, since they're both constants, I can say that that one is simply C3. And C1 minus C2, including the I, that becomes C4, because I is just square root of negative 1. Since you're basically left with just two constants, we can simplify this to have the general form of C1 e to the ax cosine of bx plus C2 e to the ax sine bx. So some of you might ask, sir, isn't it that we have two roots, m1 equals a plus bi and m2 is equal to a minus bi? How is it that we only have one answer? Yes, because this one already considers that when we combined C1 and C2 in here, and then C1 minus C2 including the I, so that's already incorporated in that. So let's go to the examples. For example, number 1. In this case, take note that this one is basically, that's your y triple prime. So this one is d cubed minus 3 d to the second plus 9d plus 13, and then all of them y equals 0. However, take note, you're given a hint, m plus 1. So, okay, so let's use synthetic division. We have 1, negative 3, 9, 13, and then, so that's 3, 2, 1, and then just constants, and then divide that by m plus 1. So let's just use negative 1 in here. So let's bring this down. 1 times negative 1 is negative 1. And then this becomes negative 4 times negative 1 is positive 4. That becomes 13 times negative 1 is negative 13. So you don't have an answer at the end. You're left with, this one becomes, by the way, let's rewrite this first. This is actually equivalent to m cubed minus 3m squared plus 9m plus 13 equals 0. So that means m plus 1 is a factor, and then you're left with m squared minus 4m plus 13 is equal to 0. So m plus 1, that's case number 1 already, real and distinct. Now, what about this one? Let's try factoring that out. M squared minus 4m plus 13 is equal to 0. If we factor this out, minus 4m, what I need is a plus 4. So I'm left with a plus 9 equals 0. So this one would give me m minus 2 quantity squared plus 9 is equal to 0. So solving for m, this is 2 plus and minus 3i. So in here, I can see that my a is basically 2, my b is 3. And then using Euler's formula, recall Euler's, according to Euler's, e to the a plus b I x gives us c1 e to the ax cosine bx plus c2 e to the ax sine bx. So c1 e to the ax cosine bx plus c2 e to the ax sine of bx. So that means, what are the three roots? The roots are negative 1, 2, plus and minus 3i. So in this case, this falls under case 1. This falls under case 3. Therefore, your solution would be c1 e to the, for the first root, negative x. I hope there's no question with that. And then for this one, c2 e to the 2x cosine of 3x plus c3 e to the 2x sine of 3x. So that means this one is your general solution. But then the tricky part in here is that you have two coefficients for x. The a goes with the exponential. The b goes with the trigonometric. The next one says b squared plus 9. And then this is basically y equals 0. I'll change the color. So that one, when we change this to a function of m squared plus 9 equals 0. So that means you have basically two roots. So plus and minus 3i. So your a is 0. Your b is 3. So what will be the solution? The general form of the solution would be c1 e to the 0x cosine of 3x plus c2 e to the 0x sine of 3x. So when we simplify this, removing the 0x, because that's just equal to 1, and the other one's equal to 1, you're basically left with c1 cosine of 3x plus c2 sine of 3x. So this one is your general solution. However, you notice on top here that you're given boundary or initial conditions. So using condition number 1, wherein when x is 0, y is 0. And then when x is pi over 2, y is equal to 1. So let's substitute those. So 0 equals c1 cosine 0 plus c2 sine of 0. So we don't have a problem with the right side because this right side gives us 0. This is equal to 1. Therefore, I can say that c1 is simply equal to 0. We don't have a problem with that. Now let's go to the second one. 1 is equal to c1 cosine of 3 pi over 2 plus c2 sine of 3 pi over 2. Earlier, we already solved that c1 is equal to 0, so we don't need to care about that one. 1 is equal to c2, and then sine of 270 degrees is actually negative 1. So I can say that c2 is negative 1. c1 is 0. So looking back at the general solution, I can safely say that y is equal to negative sine of 3x. So this is your particular solution. I hope there's none. So it's quite easy, this one. Okay, let's go to the next. For the fourth case, repeated imaginary roots. If the pair of imaginary roots a plus bi, a minus bi occurs n times, then the appropriate terms in the general solution may be expressed as C1, C2, C3, and so on until Cn. However, you'll notice that the x does not appear in the first coefficient or the constant, and then it appeared in the next, and then it became higher, and so on until it became n minus 1. So the combination is Cn x raised to n minus 1, and then e to the ax cosine bx plus the other pair, which is for the sine. So when you recall last time for repeated real roots, so recall if m, let's just say, is equal to 5, 6 times, how do we solve this before? Y is equal to c1 e to the 5x plus c2 x e to the 5x plus c3 x squared e to the 5x plus c4 x to the third e to the 5x plus c5 x to the 4 e to the 5x plus c6 x to the 5 e to the 5x. So when you notice there are 6 constant coefficients. And then how many x's are there? There are n minus 1 number of x's. This is for repeated real roots. Now we're dealing with repeated imaginary roots. So these are some examples. So let's just try the first one. So this one could be rewritten as m to the 4 plus 8m squared plus 16 is equal to 0. So you know that this one is basically m squared plus 4 quantity squared is equal to 0. Therefore, you can say m is equal to plus and minus 2i and plus and minus 2i. So it repeated. Therefore, for the first one, I can say this one, your a is equal to 0, your b is equal to 2. So what is the form of the equation, guys? Y is equal to C1, y is equal to C1 e to the 0x cosine of 2x plus C2 e to the 0x sine 2x. This is the first time m is equal to 0 plus and minus 2i appeared. What about the second time it appeared? It has to be C3, but with an x. E to the 0, x cosine 2x plus C4x e to the 0, x sine 2x. So let's fix this. So I can say C1 cosine 2x plus C2 sine 2x plus C3x cosine 2x plus C4x sine of 2x. And then some of you might want to combine both cosines. So when you do that, you'll have C1 plus C2x. Both of them have cosine of 2x plus C3. This one is C3. And then the other one is C2. Sorry for this. So this one would be C2 plus C4x. This is for the sine of 2x. So the top one, the first one here, this is for the first time it appeared. And then the second one in here, the one at the bottom, this is for the second time m is equal to 0 plus 2i appeared. All right, so this one is your general solution. So it's up to you. Sometimes it could be written in this form. Sometimes it could be written in this form. With me, sometimes it's easier to look at it this way because you know that, okay, I see a cosine, I see a sine, so that means there is the use of the Euler's formula already. However, there's C1 and another one with an X, so that means there is a repetition already. All right, so let's go to the next. So this one, when we rewrite this, this would give us m to the 6 plus 9, m to the 4, 24, m squared plus 16 is equal to 0. However, there's a hint, so we can use division. We can use, I'll use long division since it's not just linear. So m to the 6 plus 9m to the 4 plus 24 m squared plus 16 divided by m squared plus 1. So that means this one can be factored as m squared plus 1 and m to the 4 plus 8m squared plus 16 is equal to 0. So this one, let's completely factor this. M squared plus 4 squared is 0. So from the first one, you can say that your m is simply 0 plus and minus I. The second one, your m, 0 plus and minus 2i, but then it appeared 2 times. So like this. For this one, your a is 0, your b is 1. In this case, your a is 0, your b is 2, but then it repeats. So let's start with the first one. My y is c1 e to the 0x cosine of bx plus c2 e to the 0x. Instead of b, sorry. So y is equal to c1 e to the 0x cosine x plus c2 e to the 0x sine x. That is for the first set of answers. And then we'll have this one. Since it is repeated, I can say that if you want, you can say c3, c4x e to the 0x cosine 2x plus c5 plus c6x e to the 0x sine of 2x. So some of you might ask, is it okay to have c3 and c5 interchange? It's okay. They're just constants. It still depends on what you solve when you have the initial condition. So if you ask, what is the general solution? The general solution, if we arrange this, it's basically c1 cosine x, c2 sine x, plus c3 plus c4x cosine 2x plus C5, C6x, sine of 2x, because all of their a's are 0. So that is your general solution. So when you ask, this one is a combination of case 3 and case 4, because case 3, it appears only once, case 4, it's repeated.